can say is Leña Sabut Alvaro Videla. So don't expect any more Russian from me. The talk is called What We Talk About When We Talk About Distributed Systems. And it's kind of an intro to the topic of distributed systems. And I choose these colors because I gave this talk for the first time in Sweden. So I also call it the distributed system for the IKEA family. I don't know, you know what is IKEA, I guess. So I need to look back because I have no idea what is the next slide. So distributed systems. There. The definition of distributed system is by Leslie Lamport. For those that don't know, Leslie Lamport is kind of the founding father of distributed systems. I don't know if I can say this, but he's the Lenin of distributed systems. And he says, a distributed system is one in which the failure of a computer you did not even know existed can render your own computer unusable. So it's about things that break, and we have no idea why they break. So please work, yeah. For example, in the internet, Facebook goes down and the whole internet stops working because no more like buttons, no more share, no more anything. And if you are a programmer, you know that when GitHub fails, you cannot work anymore because GitHub is a distributed system, and it ended up being a centralized system, and then, yeah, we cannot work anymore. It's sad that this happens. So the problem when you try to learn about distributed systems is that there is a lot of jargon, a lot of words that they don't necessarily mean what they mean in a different area of computer science. The definition of jargon from Google is special words or expressions that are used by a particular profession or group and are difficult for others to understand. So when we have a distributed system, we have many entities which are trying to solve a problem. So you have many computers, many phones, many Internet of Things devices, whatever. They are called either nodes or processes. They have partial knowledge, and there is the problem of uncertainty. So whenever we talk about distributed system, we talk about having many computers probably connected over the network, which each computer has partial knowledge of the whole problem that they are trying to solve, and there is an uncertainty. You never know what the other computer actually knows or doesn't know. And it's a deep, deep rabbit hole if you want to start learning. Like, what do you read? Where do you start? So there are a lot of papers, and you need to know which one you can read. This one is impossibility of distributed consensus with one faulty process. This is one of the main papers of distributed systems. It's called FLP. Usually because the authors are Fisher, Lynch, and Patterson. So by the first letter, the people call this paper FLP. And many people will tell you, many developers, if you don't know FLP, just get out. Like we were talking yesterday with Dimitri. You don't know this? Out now. Why? Why is this feeling? I don't think this is correct. Then there is another one, which is by Leslie Lamport. It's called the Part-Time Parliament. This one is the actual Paxos paper. I don't know if you know this algorithm for consensus. Again, people will tell you, you don't know Paxos? Out of the room. Why? I don't like that. The other one is called Time, Clocks, and the Ordering of Events in a Distributed System. This is the main paper or the kind of original paper of distributed systems when the concept of time is explained in distributed system. Again, if you don't know that paper, get out of the room. No, again, that is wrong. And another one, Simple Totally Ordered Broadcast Protocol. This is a paper about Zookeeper. I don't know if people working in Java or using Kafka, you know Zookeeper. That's the paper from the algorithm. And recently, there is one called Raft, or In Search of an Understandable Consensus Algorithm. So there are a lot of papers. People will always tell you, if you don't know this paper, you are not worthy of being here. And I started questioning myself, why should I know this? Why maybe you are not working with some of these things, and there is nothing wrong with not knowing these papers. But anyway, there are a lot of them, and the day only has 24 hours. You have to sleep, eat, and work. When are you going to read all these papers? There are also books. This is from my library, which is an IKEA library. You can see a lot of titles. For example, the first one on the left, it says Programming Distributed Computing Systems. When I saw that book, I bought it. It's from MIT. I say, okay, maybe it's a good book because I want to learn how to program distributed systems. The book has nothing to learn about distributed systems. It's a book that is teaching you about research programming languages from MIT. Like you learn lambda calculus, pi calculus, and all this stuff that, who cares? Then there is, for example, the art of multiprocessor programming, not related. This is about concurrency on the CPU, for example. This one, the third from the right, distributed algorithm for message passing systems. I was working in Erlang, in RabbitMQ. This is the distributed algorithm. I maybe need this book. Message passing, Erlang does message passing. So it seems to be the book to buy and learn. That book doesn't consider failure. The book assumes that every algorithm will always be successful. So how can you put this in practice if there is no failure cases? Computers never fail for that book. So good luck with that. So there is a lot of material to choose, but who knows where to start? And then there is the question of why. Why do you even care about this? Why are you even sitting here? There's probably somebody else talking somewhere more interesting, and in Russian maybe. I don't know. That could happen if you don't read the theory. The problem with distributed systems is that it's too complicated, it's too complex, it's too difficult. It's very difficult to prove that the algorithm is going to work, that you're not going to lose data, for example. And if you try to invent your own algorithm, if you try to solve this problem on your own, you maybe end up with something that doesn't fit correctly. Please, this is a distributed system problem. This thing doesn't know what the other thing wants. So, in distributed systems, there are different models, and this is the problem where I want to dig into. When you work in distributed systems, there are different models on how the computation are going to be analyzed or studied. There is a timing model, an inter-process communication model that is used for the nodes, and then there are failure modes. You maybe grab the Raft paper or this FLP paper, the first one I mentioned. If you don't understand what these three things are, you don't understand the paper. Even if you think you understand the English written there, some words don't mean what you think they mean. And I will show you why. So there is a timing model, and there are two major models here. One is the synchronous model, the other one is the asynchronous model. I don't know what you understand for this, but if you work in Java, for example, you have Netty, which is an asynchronous framework, and you have the old way of doing I/O, which is synchronous. If you work in Node.js, you have the way of having all these callbacks for doing asynchronous computation. One speaker yesterday was telling me about his talk where he's going to present something like this for Python. Actually, these two words here have nothing to do with what I just tell you. Synchronous in a distributed system, it means that you know for the algorithm exactly how long it takes for a node to execute one step of the algorithm, you know exactly how long it takes for a message to go from one node to the other node in the network, how long this other node takes to process the message and reply back. That is a synchronous system in a distributed system context. The asynchronous model is totally the opposite. You have no idea how long it takes for a node to process a message. You have no idea how long it takes for the message to go over the network. And there is no way to tell how long the other node will take to process that message. What problem can arise in this context, asynchronous model? I have no idea to tell if the other node in the network is alive or not. Because is the node being too slow? Is it dead that is not replying? Okay, I can add a timeout. Let's add a timeout of 1 minute. If the node didn't reply in 1 minute, then it's dead. What happens if the node replies after 61 seconds? All this uncertainty is part of the asynchronous model. So when we talk about synchronous or asynchronous, it's not this asynchronous computation kind of thinking like net in Java or Node.js, let's say. It's about what happens in the algorithm with each step if we know if there is a bound in the time. And there is one that is not so much used in the research, which is called semi-synchronous model, where it's mixed. But yeah, there is not so much written about this one. I have a question you don't need to answer. Do you think the synchronous model exist in reality? Raise hands. Do you think the synchronous model exists in reality? No, don't know, don't understand the question, or? Okay, he says he does it, yeah. The synchronous model maybe only works in real-time computing, like on a car or on an airplane, stuff like that, when there are times to know exactly when things happen. But in computers like the ones we use every day, this doesn't exist. There is a reason why they have it. If you prove that even on the synchronous model you cannot solve a problem, then you probably cannot solve it in a synchronous model. We will see later why it's important to know that this exists. The other part is the inter-process communication. There is either message passing or shared memory. I think these words are what everybody understands they are. And then it's important to know on which failure mode the algorithm falls into. Maybe for the particular problem you have, an algorithm doesn't fit this failure mode. So there is one called crash stop. It means this node that is taking part of the algorithm is just, let's think you want to replicate data. You want to know that data went from node A to node B. Those are the nodes I'm referring here. Or you have like the ATM, the bancomat, and you have the bank central. Those are the different nodes I'm referring here. In the crash stop model, the node just crashes and it's gone. If you have an algorithm when the node comes back alive, then it's not this model. But this model is the easiest one to reason about, because if a process is gone, you don't need to recover data, you don't need to reboot the node, it's just gone. Then we have crash recovery. A node can crash, and maybe from persistent storage can come back and recover the state, for example. I think Raft falls into this category, crash recovery. Then we have omission faults. Here, a node may not reply to a message, or it may not even receive the message, or it can do both. Why it matters to say there are these distinctions? You can have a cache system where every request reaches all the nodes, so the nodes will be up to date, let's say. But one of the nodes is not replying to the other node, telling them, I process this particular request. So it's doing reply omissions, but not receive omissions. What happens? If you then try to retrieve information from the cache, it's fine, because that node is still up to date. The other nodes in the system maybe don't know that the node is up to date because it's not replying requests, but at least as a client of this distributed system, you can still use that node. So that's the difference between the various kinds of omission faults. And the last one is the one I like to call the living la vida loca version, because here, everything that you have in your nightmares, it can happen in your distributed system. Arbitrary failure mode can be that from normal failures of computers to a computer pretending to be working properly, but behind the scenes doing something wrong with the algorithm. Let's say there is corrupted memory or something like that. There can be somebody that got into your system like a hacker, and they are impersonating a node, so they are pretending to work properly in the system, but behind the scenes they are collecting information. I think we heard about this in the news. They call it NSA lately. You probably know about that. They can be in the system collecting data. Nobody knows this is happening. There you have Byzantine failures. And it's very hard to program solving problems for this model. And there was a research from Yahoo where they said, usually you don't need to care about that failure mode, because we're working in networks that are close to the outside world. So if algorithms go up to crash recovery, usually they are fine. They say it is too expensive to cover for Byzantine failures in the computing resources that it will require. So I think we have time, because I don't know if I have enough time to cover everything. So if you have questions, let me know, but I don't know if there is enough time for that. Another thing that you will see a lot mentioned in papers is this liveness and safety. That's the paper that introduced these concepts. And an algorithm will tell you, we have these liveness properties, we have these safety properties. Safety means that some bad thing does not happen during execution. For example, communication links should not invent messages out of thin air. That's safety. It's telling you that the algorithm assumes that this, for example, will not happen. And liveness is kind of the opposite. It's telling you a good thing happens during execution. So, for example, a destination process eventually delivers the message. Oh, let me backtrack a bit. So in liveness and safety, they usually take, like as an example, a data structure. Imagine you have a queue. A safety property of a queue, of a distributed queue or concurrent queue, is that a queue is first in, first out. A safety property is that the queue never returns a message out of order. That could be a safety property. And a liveness property will be that you will obtain a message, that you will not like time out or I don't know. So we need to also be careful on what these things are when we try to study an algorithm and say, can we use this in our company or not? Or can I try to implement this or not? So let's take a look at this paper, FLP. The paper is called Impossibility of a Distributed Consensus with One Faulty Process. Why this paper is important? In 1980-something, they were trying to solve the consensus problem, and they were trying many different kind of solutions, but it was until this paper that they proved that if you have one faulty process, you cannot solve consensus. Consensus is the problem of agreeing on a common value. For example, if you have a database that is distributed and you need to do replication, agreeing if the nodes needs to commit the transaction, that's a consensus problem. Some coordinator in the transaction will start the transaction and say, can we commit this to the file system? All the nodes will vote, that's why it's called consensus. And if they reach consensus, they will either commit or cancel the transaction. They prove this is not possible. So imagine that the main researchers of distributed systems in the 80s were trying to solve a problem, and at least somebody came and said, no posible, as they say the gringos when they fail to speak Spanish. I'm a Spanish speaker, by the way. It's like me trying Russian, probably. So in the abstract, we have the consensus problem involves an asynchronous system of processes, some of which will be unreliable. Here, if we don't know what asynchronous means, as I explained before, there is no timing for operations, no timing for messages traveling in the network. The first sentence already, if you don't know what that means, you have no idea what the rest of the paper is about. If you think about asynchronous computation as I send a query to the database, I keep doing something else. When the query comes back, I do something with the query, for example. That's not asynchronous as is mentioned here. Okay, the problem is for the reliable processes to agree on a binary value, like commit, not commit. And we show that every protocol for this problem has a possibility of non-termination, even with only one faulty process. So they are just explaining what problem is not solvable. And for the time, it was like, in this paper, we show the surprising result that not completely asynchronous consensus protocol can tolerate even a single unannounced process death. And look at this. We do not consider Byzantine failure, so they are not that down in this failure mode. And we assume that the message system is reliable. Yeah, right. And it delivers all messages correctly and exactly once. That's also not going to happen in the real world. But even with those restrictions, they have a reliable message system. Imagine having a TCP connection that doesn't drop messages. They are assuming this happens in the real world. There is no message loss. This is not true. And all the messages are delivered correctly and exactly once. So they put all these restrictions. They live in this ideal world, which is not our world, and this problem is still not solvable. So don't try to go and achieve this kind of consensus. It won't happen. And they say, like, yeah, nevertheless, with all these assumptions, even if you stop one, you cannot have a distributed commit protocol and blah, blah, blah. I'm not going to make you go to sleep with this. One thing they say is they don't have any kind of synchronized clocks, because you can say, okay, I can remove this asynchronicity by putting a clock, but then you're cheating. You cannot have clocks here. It's a fully asynchronous system. Go in, please. So a question you may have is even, what is consensus? Before I get there, point was, if we don't know all these words they are trying to mention here, like what it means to be delivered, what it means to be, for example, to deliver a message in distributed literature, it means that the node received the message. If you read a node delivers a message, it means that the message is already on the message system and the node takes the message and does something with the message. So here, every message is eventually delivered. It means every message is actually retrieved from the message system. So I can tell you all this. They like to complicate things with the words. So what is consensus? Consensus is whenever you have an agreement problem, you have a consensus problem. And I have a question. Who said this sentence? I'm not sure in this side of the world you would know. But do you like the sentence? Do you don't like it? Do you want to throw something at the screen? There is a growing tendency to replace the concept of truth with that of consensus. This was said by the previous Pope. And this guy, because if you are, I don't want to, this is nothing against the church. I don't care about the church. But there is, in our way of thinking about the world or way of seeing the world, we want to have truth, like absolute truth. And there is a philosopher from Italy called Umberto Eco. He died actually like 1 month ago. And he quotes the Pope saying that this is kind of a very religious idea that you have this truth, like this God that knows everything. But in reality, it's impossible to know everything. And this is very relevant to distributed systems. You have all these nodes, and you want them all to agree in something. But when you have physics, and you have the speed of light, and you have information traveling across the network, you will never have truth. It's impossible to have a universal truth in a distributed system, because physics goes against that. There is a delay of messages going through the network, and so on. So we may have this old antique idea of truth, because most of our societies were kind of religious 100 years ago, but yeah, it's not going to work in reality. Next. What are the properties of consensus? There is the termination property. Every correct process eventually decides on some value. Validity, if a process decides V, then V was proposed by some process. I will tell you what this means. How you say please in Russian so these things understand? An agreement. Not two correct processes decide differently. So what I'm even talking about here. When you have consensus, at some point, the decision has to be made, termination. If you are running elections, at some point you need to choose a president, right? You cannot keep running the election forever. They say everybody votes on, I don't know, in my country is the last Sunday of November. By the last Sunday of November at 6 p.m., if you didn't cast your vote, algorithm is over. Validity. If I don't propose myself for president, nobody can vote for me. If a process decides B was proposed by some process. An agreement, not two correct processes decide differently. Here is a bit different from an election, but it's saying that if a process is correct in the algorithm, it hasn't crashed or it hasn't had any kind of error, it will arrive to the same conclusion as the other processes. So if they say, should we commit this transaction to the file system? If the process is correct and every other process says, yes, we do, then all these processes will commit the transaction. Do I need to call Volodya for this to work? Or I have his number if you... There are many Volodyas, so... And there is also uniform consensus, which here is a bit more restrictive, which says no two processes, correct or not, decide differently. This is a bit more difficult, but yeah, it's a different flavor of consensus.
Maybe a better way.
Can somebody go to the next slide? Move it.
Are there anyone? Там кто-нибудь слайды листает? Можно листать слайды?
Now it went. Okay, thanks. I need a mirror somewhere here. It's receiving the commands in you see, asynchronous system. There you have it. So we need consensus when? When do we need it to have this? When a set of processes, okay, go back, not so fast. When a set of processes have to agree to take a common action. And if you need to do atomic broadcast, like you need to send a message around the network, and this message has to be received by every node in the same order, then you're trying to solve atomic broadcast. And this problem is a sub-problem of consensus. And group membership, if you need to know which nodes are part of your distributed system, that is also a consensus problem. Why do I tell this? Tomorrow, maybe we don't know about consensus, we don't know about FLP, but somebody tell us, you need to implement with Gossip or with something a group membership algorithm for this replication we are trying to implement. And we need to be this, and these properties. So you start working on that. You have no idea. It's a sub-problem of do whatever you want of consensus. And we will waste a lot of time when probably this is no solution, because as we know, there is this FLP paper that mathematically proves that this is not possible. So we will just waste time from the company trying to do something that is not doable. Or if you are studying a PhD or a master's, you will write a thesis that will never be finished. So, okay, this is the definition of atomic broadcast. Correct processes deliver the same set of messages in the same order. If you want to do that, you also need to do it using consensus. Why will you care about the atomic broadcast if you need to replicate messages across a network of nodes? Like in RabbitMQ, for example, they need to replicate messages in the cluster, so they need some form of atomic broadcast. And sadly, that algorithm is kind of home-baked, and it kind of didn't take into account this problem. So use it with care, I would say. So FLP tells us that if consensus cannot be achieved, then atomic broadcast or group membership cannot be achieved either. So what do we do? Assuming this. We pack our bags, go. There is nothing to see here. We cannot solve consensus. Why am I wasting your time? I mean, you can go play FIFA on the second floor or third floor, I guess. So why? There is this paper, which is called Stumbling Over Consensus Research, Misunderstanding and Issues, by this guy, Marcos Aguilera. And I'm going to start crying, but I don't know, in Russia, men don't cry, right? Is somebody changing there, or, okay. Stay there, please. So, you see, we don't synchronize our consensus protocol. This is going very bad. So, stumbling over consensus research, this paper by Marcos Aguilera, there is a problem. This guy used to work for Microsoft. When he left Microsoft, all the papers were removed from the Microsoft website. So all of this is 404 if you try to read it. But there is a book, they are publishing a book. I know you can buy books in Russia online, so you can try to find the book where this paper is. And he explained that the problem with the impossibility result like FLP is not a mathematical in the sense of the impossibility result like from Erdos or Alan Turing and whatnot. The problem here is that it's impossible to solve consensus under very specific situations, like if your process is never scheduled by the CPU, then it will never fetch a message from the network and it will never make the algorithm progress forward. You can be very unlucky, and this may happen to you that under I don't know what kind of circumstances, your process is never scheduled to do that. But then think from the other point of view. You are having 10,000 requests per second. That's like 1 billion per day. Are you going to try your luck and see if your CPU is scheduled this process or not? FLP is telling you that if this happens, you don't solve consensus, and it will happen sooner or later. So he says, it's not exactly an impossibility, but don't try your luck. And there is failure detectors. This is the way to solve consensus. You introduce failure detectors into the system and try to see if the other nodes are down or why they are not progressing with the algorithms. Cassandra uses this. I think Cassandra has like a broken failure detector for the problem it's trying to solve. Because Cassandra is trying to replicate data from 3 nodes and is doing, let's say node A is trying to connect to node B, but cannot do it. But node C is telling node A that node B is alive. But if node A cannot talk to node B, it doesn't matter that node B is alive or is not alive, because you need to be able to communicate with that particular node. In the failure detector implementation in Cassandra, for what I understand, they do this kind of transitivity that actually is kind of useless. Anyway, failure detectors. So, there. This is the paper that introduced the whole concept of failure detectors. And next. More next. There. So failure detectors are external processes to the algorithm. They provide information about suspected processes, and completeness property, it means crashed processes are detected. So if you have a failure detector, they will suspect other elements of the algorithm, and they will tell when they are crashed, they will be completely suspected. And they have accuracy. Correct processes are never suspected. So if you haven't failed, then you won't be suspected. And this is called, you have a problem, you just go and rub some perfect failure detector into your problem. This doesn't work either in reality. Do you think it's possible in reality to detect if the other node has never failed? What did we say? You have a timeout of 60 seconds. The node reply after 61 seconds. The node was still alive, but you suspected the node alive, and you mark the node to be dead because it didn't reply in a minute, and it was actually alive. So to implement a perfect failure detector on an asynchronous distributed system is not going to work. So did I just turn off the slides, or what happened now? So there is a thing which they call this is the implementation of the perfect failure detector. Why do you care again? Why do you care about synchronous system if you cannot have them? Why do you care about perfect failure detectors if you cannot have them? Because it's trying to show you, if you want this kind of perfection, you need a synchronous system. A synchronous system doesn't exist. Therefore, you are not going to have that. You need to be happy with the eventually accurate failure detector, which will try to eventually, every process that crashes will be permanently suspected by every correct process, and accuracy, there is a time after which some correct process is never suspected. What does it mean? If your node fails, sooner or later it will be discovered. If your node is suspected of having failed, but it haven't failed actually, sooner or later will be brought back into the network and saying, yeah, you can still participate in the algorithm. Like, why don't you come to vote? It's about to be 6 p.m. If you don't come, you cannot vote. And I keep calling you and trying to get you to vote. And they say, okay, maybe this guy is dead. Is that why he's not coming? But then you show up 1 minute before time to vote. So it was eventually a weak accuracy. I was suspecting that this other guy was dead. He wasn't actually really dead. These algorithms will try to give you this kind of certainty about what's happening in the distributed system. And there is where you can read. Again, this slide, maybe you say, oh, this guy is just throwing random concepts around, but I can tell you these are probably the main concepts you need to learn. If you want to dive deep, then there are all these papers I'm trying to give you to go deeper on each of these areas. So that's the paper, and I'm not going to go with quorums because there is no time. Too fast? No? Okay, more. Consistency, there is no time. One thing, keep in mind, do you know Kyle Kingsbury, Afir, Shepson, the one that tests databases? He's testing for linearizability. There are many kinds of consistency models. I'm not going to cover them here, no time, but be careful. Maybe the problem you want doesn't need linearizability. So that something failed the linearizability test doesn't mean it doesn't work for you. You need to understand what these consistency models are to really know what is Kyle trying to tell you, basically. I'm not going this, next. There's all the models. You can read on that particular book. And now books. Before finishing, I want to show you books and tell you if you want to buy them or find them online or whatever you do. There is this one, Distributed Algorithm for Message Passing System. As I said before, this book doesn't consider failure. So it's a really good book for beginners to know all the concepts like time, spanning trees, how to build them, how to avoid deadlocks, consistency models, vector clocks. All these things are in this book, but they don't consider failure. If you already know all these things more or less, maybe this book is not the right one. Depends. If you are programming in Erlang, it's really easy to understand the algorithms here because they're all using message passing. Next. There. So when you reach the last page of that book, the author will tell you, but I brought 3 more books. You can buy them and make me richer. So this is fault-tolerant agreement in synchronous message passing system. Yeah, fault-tolerant, computers fail, but the systems now are synchronous. So again, it kind of helps, but not so much. The next book by this guy is Communication and Agreement Abstraction for Fault-Tolerant Asynchronous Distributed Systems. This is a very good book. It will give you an overview of consensus for all these problems that we may be having in the real world. This is like the Bible of distributed algorithms. It's written by Nancy Lynch, the L on FLP. She was the one that wrote that paper, FLP. And this will give you an overview of all these models, all these timing models, communication models, everything. But it's kind of a no book in the sense that it doesn't have real code. It has like pseudo code, and it's a system that is only used by her. And like her students maybe only use the notation that is on this book. It's the I/O automaton or something like that it's called. So it's an interesting book. It's very academic, I would say. If you want to buy a book, this book is that one. Reliable and Secure Distributed Programming is the only book that talks about security in distributed systems from all these I've seen. It will give you an intro to all these different models, and it will talk a lot about consensus and whatnot. This book is highly recommended. And this one, if you Google what this guy did, do you know Kenneth Bierman? Probably not. This guy, if you Google what this guy wrote, the name of his protocol, you probably end up in jail. Why? He wrote a protocol called ISIS, like the terrorists. And this protocol, was used in the 80s to control airplanes. So I'm not making a joke. They have a protocol called ISIS to control airplanes. It was heavily used in the 80s in the air industry to control all the flights. And he was kind of one of the pioneers on this consensus message grouping. Today, he's researching gossip, stuff like that. The second half of the book is very interesting because it will go through his protocol, through Paxos, and coming into, like from the past, from what happened in the 80s until what is current today. So, second half of the book is very, very interesting. Replication, lot of papers. This is like what is current research on replication, highly recommended. Finding non-paywall papers. If you need to find papers and they are behind a paywall, like on the ACM, usually the author university website, they have the papers for free. And conclusion. As you can see, probably you are all wanting to leave this place now and eat something, take a coffee. This is a deep rabbit hole. There is a lot of topics to cover. Is computing science where science is still a thing? This is something I like in distributed system, or you prove your thing or get out of the room. We don't want theories that don't work, let's say. The history of the field matters. You cannot just say, I invented a new algorithm for replication. Okay, what happened with this one, this one, this one, this one, and this one? If you don't explain why your algorithm is better than all these other ones that are already used in the industry, your paper will probably be rejected. Nobody will care about your paper. And finally, yeah, there is a lot to read, and read more. So, spasibo, and thanks.